Welcome to today's session. I am pleased to present this architectural framework designed for secure service-to-service authorization. Our focus today is on implementing relationship-based access control, or ReBAC, utilizing SpiceDB within an Azure Kubernetes service environment. As you can see from the central diagram, this model places robust security at the heart of the system, governed by the foundational pillars of Zero Trust principles. We are moving beyond simple role-based models to a more granular, relationship-driven approach. The interconnectivity between our API layers, Kubernetes orchestration, policy data, and underlying cloud infrastructure ensures that every service interaction is verified and authorized. This guide serves as a blueprint for organizations looking to scale their security infrastructure while maintaining high performance and strict access control across complex distributed systems.
The modern authorization challenge lies in the inherent limitations of traditional role-based access control at scale. As illustrated on the left, ReBAC systems often suffer from role explosion. Because permissions are tied to static roles, these systems struggle to adapt when operational context changes dynamically. This leads to several critical issues: an inability to effectively represent nested hierarchies, significant data duplication that causes security drift, and a general fragility within ephemeral environments like Azure Kubernetes Service. The solution to these challenges is relationship-based access control, or ReBAC. As seen on the right, ReBAC utilizes graph-based logic, where permissions are computed based on the actual relationships between entities. This approach enables transitive permission inheritance, easily managing complex structures like groups within groups. In a ReBAC model, authorization decisions are the result of efficient graph traversals rather than linear list checks. This architecture provides the real-time consistency and scalability essential for modern, distributed microservices environments.
SpiceDB serves as an open-source implementation of the Zanzibar paper, acting as the central intelligence for authorization across an entire infrastructure. As illustrated, disparate services such as Service A, Service B, and Service C all communicate with SpiceDB, frequently referred to as the brain, to perform permission checks. The core of this system relies on a parallelized graph walk, which allows complex relationship-based access control to be resolved with high efficiency. Three foundational pillars define the SpiceDB architecture. First is the concept of a centralized truth, which ensures that every internal request is validated against a single, scalable source. Second, it provides horizontal scalability by dispatching checks across multiple nodes to maintain millisecond latency at scale. Finally, SpiceDB ensures strict consistency by utilizing Z tokens to solve the new enemy problem, guaranteeing that authorization decisions are always based on the most relevant data. This slide outlines our infrastructure topology and deployment strategy on Azure Kubernetes Service. To ensure optimal performance and reliability, we have implemented a multi-zone strategy, utilizing dedicated node pools for different workloads. In Zone A, we maintain the application node pool. This pool is dedicated to our microservices, providing necessary isolation that prevents resource contention between our core application logic and other cluster services. In Zone B, we have established the authorization node pool, specifically designed for SpiceDB. The lifecycle of this component is managed through the SpiceDB operator, leveraging the SpiceDB Cluster Custom Resource Definition, or CRD, for automated orchestration. From a networking perspective, the SpiceDB pods are configured with specific Kubernetes annotations to utilize an internal Azure load balancer. By setting the internal load balancer flag to true, we ensure that the service is assigned a private IP address, maintaining secure and efficient internal communication within our network perimeter. SpiceDB is designed as a stateless service, which means its resiliency and persistence are determined by the pluggable data store you choose to implement. Depending on your specific deployment requirements, there are three primary paths to consider. For development and testing purposes, an in-memory data store provides an ephemeral solution with zero setup requirements, though data will be lost upon restart. If you are operating within a single region on AKS, Postgres, specifically Azure Database for Postgres Flaskable Server, is the recommended choice, as it is optimized for operational simplicity. For high-scale or multi-region deployments, CockroachDB is the ideal fit. Its distributed architecture mirrors that of SpiceDB and includes built-in geo-replication to ensure global availability and performance. Identity and trust within our architecture are built upon a secure authentication handshake.
Operating under a trust no one model, we decouple the two core security concerns. Authentication is handled via Azure, while authorization is managed through SpiceDB. The sequence starts with the service requesting a token from Azure OIDC. Azure returns a signed JWT, providing the workload with its unique identity. With this identity in hand, the service makes a gRPC request to SpiceDB, passing the JWT as a bearer token. Before processing the request, SpiceDB must verify the sender's identity. It does this by validating the JWT against the OIDC issuer. This validation process is configured through specific flags, as shown at the bottom of the slide, where we define the OIDC issuer URL and the intended audience to match our specific Azure tenant settings.
In this slide, we examine the transition from role-based logic to relationship-based access control. On the left, our schema definition for a service establishes two foundational relations, caller and owner. The call permission is then derived from these relationships. Access is granted if the requester is a defined caller or a member of the owning team. The diagram illustrates how these entities interact. By linking a user or service to a team and that team to a specific resource, the system can dynamically compute permissions across the graph. This model is particularly powerful because it natively supports recursive permissions and nested groups, allowing for complex authorization structures without additional overhead or manual logic. Solving distributed caching challenges requires a robust approach to consistency. SpiceDB addresses the new enemy problem through the implementation of Z tokens and snapshot consistency. When a write event occurs, the system generates a Z token, labeled here as T1, which represents a specific point in time. This token is returned to the client and serves as a causal marker. When the client subsequently initiates a check event, it includes this token in the request, using the at least as fresh parameter. This ensures that the query is evaluated against a database snapshot that is at least as recent as the write at T1. By following this workflow, we achieve a guaranteed data freshness of T1 or greater, successfully balancing high-performance caching with the requirement for causal consistency. Integration pattern A focuses on the use of application-side gRPC interceptors to enforce authorization. When an incoming request arrives with a bearer token, it is processed by a middleware interceptor. This interceptor performs two key steps. It extracts the subject from the JWT and then executes a gRPC check permission call to SpiceDB. Depending on the SpiceDB decision, the request follows one of two paths. If there is no match, a 403 forbidden response is returned immediately. If a match is confirmed, the request proceeds to the application handler and business logic. To implement this pattern, developers can leverage official auth-sed client libraries for Go, Python, and Java. Integration pattern B focuses on leveraging a service mesh, specifically Istio and Envoy, to achieve zero-code authorization enforcement. By utilizing sidecars within a Kubernetes pod, we can offload authorization checks entirely to the infrastructure layer. In this architecture, the app container sits alongside an Envoy proxy. When traffic is processed, the Envoy proxy intercepts the request and initiates an external authorization call via the ext-off-c filter to a dedicated auth adapter. This adapter communicates with SpiceDB to determine if the action is permitted. If the request is approved, traffic flows back to the application. If denied, the request is blocked at the proxy level before ever reaching the application logic. This pattern ensures a clean separation of concerns, allowing developers to focus on core functionality while the infrastructure handles security and policy enforcement. Operational excellence in performance tuning requires a strategic balance between resource allocation and system stability. As illustrated, we manage database interactions through distinct connection pools for read and write operations to ensure predictable behavior under load. In this specific configuration, the read pool is operating at 70% capacity with a maximum of 30 open connections, while the write pool is at 50% with a limit of 20. A critical constraint to observe is the relationship between these local pool sizes, the number of service replicas, and the total database capacity. Specifically, the sum of the read and write connection limits multiplied by the total number of active replicas must always remain below the database's maximum connection threshold. Maintaining this overhead is essential to prevent connection exhaustion during scaling events. To further refine performance, we can adjust the quantization interval.
This allows us to navigate the trade-off between maximizing cache hit rates to reduce database pressure and maintaining the real-time freshness of data for the end user. Depending on the specific requirements of the service, fine-tuning this interval can significantly improve overall throughput. Resilience and observability are maintained through the monitoring of three primary metrics. First, dispatch latency measures the time required to resolve subproblems across cluster nodes, where the objective is to consistently remain within the millisecond range. Second, we monitor data store wait time using the PGX pool empty acquire metric. Our target for this metric is 0, as this ensures we avoid database starvation and maintain fluid data access. Third, check throughput tracks the total number of check permission calls per second, providing a clear view of the system's operational load. These metrics are exposed on port 9090, allowing for seamless integration with Prometheus and Azure Monitor to ensure comprehensive system oversight. Security hardening and best practices are foundational to our infrastructure. We approach this through 4 key pillars. First, we implement a fail-closed policy. Our schema is strictly additive, meaning the absence of an explicit permission results in a denial. This ensures our default posture is always secure. Second, we apply the principle of least privilege. Our SpiceDB pods are configured to run as non-root users and utilize read-only file systems, significantly reducing the attack surface and potential impact of unauthorized access. Third, we are transitioning to secretless authentication. By moving from pre-shared keys to Azure Workload Identity, we eliminate the need to manage static secrets, instead leveraging secure, identity-based access. Finally, we embrace schema as code. We integrate schema validation directly into our CI/CD pipelines using zValidate. This ensures that every schema change is thoroughly vetted before it ever reaches production, maintaining the integrity of our security model. To summarize, this architecture provides a comprehensive foundation for Zero Trust by integrating security across 3 key layers: the infrastructure, the logic graph, and the application interface. Our approach focuses on 3 core pillars. First, it is resilient, replacing traditional, brittle ReBAC lists with dynamic, relationship-based access control graphs that scale with your environment. Second, the system is highly performant, achieving millisecond latency through parallelized dispatch and the use of Z tokens for authorization checks. Lastly, the solution is native to the cloud ecosystem, offering seamless integration with Azure Kubernetes service via specialized operators and workload identity. Together, these elements provide a robust, high-speed, and easily managed security framework for your AKS workloads. To further your understanding and implementation of SpiceDB, I have compiled a list of key references and documentation. First, for operational guidance, you can find the SpiceDB operator documentation on our website. This resource is essential for anyone looking to manage SpiceDB deployments within their infrastructure. For those diving into permission modeling, the schema language reference provides detailed specifications on how to define your authorization logic. If you are interested in the academic foundations of this technology, the Google Zanzibar white paper is a seminal read that outlines the architecture SpiceDB is built upon. Lastly, for developers ready to start coding, our official client libraries for Go, Python, and Java are available on GitHub under the auth-zed organization. These tools will help you integrate SpiceDB into your existing applications seamlessly.